by hand a little bit until it makes sense, and then once it makes sense, you can run the machines to get the do the heavy lifting for you. It's a pedagogical bastardism. It's kind of okay. All right, so flock number 4. Flock number 4, we got 4 birds. I want to go back to Zach's awesome comment from earlier. I mentioned Max buying 2 birds, and he came back with 1.8. I love that connection, because we did learn something yesterday. Since each bird has a 90% chance of being a female, that means essentially every bird is 90% female and 10% male. I mean, on average, right? On average. Which means that every bird I buy contributes 0.9 girls to my flock. So if I buy 1 bird, I average 0.9 girls. If I buy 2 birds, I average 1.8 girls and 0.2 boys. If I buy 3 birds, I average 2.7 girls and 0.3 boys. 3.6. Oh, good, for 4. For 4 birds, the average will therefore be 3.6 girls per 4 birds. So essentially, every single time you add a bird to this flock, you add 0.9 more girls to your flock, on average. On average. Now, I got 4 girls. Does that mean that I'm significantly different from average? No, because it's only 4 girls. It's not on average over time. It's my flock right now, right here. I still got those 4 new ones that I haven't seen fully developed yet. And I almost didn't see Gretchen fully developed, but I found her last night. So we'll see what happens with those 4 as they get older and maybe lay eggs or start calling at 4 o'clock in the morning. I have to get rid of the rooster. Okay? Good. So that's your average. So you know what the average is right off the bat. Fantastic. What does your distribution look like? I got an X and I got a P of X, yeah? What am I interested in over here?
Number of girls.
Number of girls. Love Michaela, thank you. So Jen gives us number of girls, which is what we want, yes. Number of girls. The values? 0 to 4. Because that's what you could have. If you buy 4 birds, they might all be boys. You might have 1 girl and 3 boys, 2 and 2, 3 and 1, or that's what we wanted anyway. We wanted all 4. Because we want to go to eggs, not roostering. Okay, which probability did you guys grab first?
0.
0? Yeah, probably the easiest one, right? Or one of the easiest ones. And what is the chance? So if I'm looking at that little box with 4 marshmallow peeps in it, what's the chance they're all boys? 0.1, Michaela, thank you to the 4th power, huh? 0.1 times 0.1 times 0.1 times 0.1. Highly unlikely, yes? 1 in 10,000. There's a 1 in 10,000 chance, which means, I'm going to say this probabilistically for you. If I send Max into the store to buy 4 birds 10,000 times in 1, exactly, okay, weird dude. But what that means is, in 1 of those 10,000 times, he'll come out with 4 roosters. So should we expect that? No, because it's so rare. That's going to be an outlier to get 4 roosters, assuming that they're actually 90% girls. Good. All right, good. What'd you do next?
0.9 times 0.1 to the 3rd.
Oh, good. So Sarah, you did this one next. You went right on the line. Good, good. So 1 girl, 3 boys. So you got 0.9. That's the girl. And then you got 3 roosters, yeah? So 0.1 cubed.
Times 4.
And then I hear times 4. I want to do those in a different color. The numbers that come out front here are pretty special in my book, and I'm going to talk about them more in a little bit. I made a whole quiz about them for next week. So for next week, you'll see, I think there are 3 quizzes posted for next week. One of them is about just these numbers out front, and I think you'll see why there's some deep mathematics behind it, if you're interested. So you can take a look at that. So everybody see why it's 4? Describe to me why it has to be 4.
Because you do that 4 times.
Why?
Because you do boy, girl, girl. I mean boy, girl, boy, girl, boy, girl.
Because all you know is there's 1 girl and 3 boys, but you don't know who the girl is. It could be Bertha. Or it could be Marge. Or it could, you know their names yet?
Yeah.
Nancy. Hey, Gertrude's not in here. Gertrude's one of the new ones. It's Bertha, Mary, Marge, Nancy. That's our grandmothers. So, because you don't know which one it is, you have to account for all the possibilities. There's only one possibility that they're all roosters. They're all roosters. It's like snake eyes. There's one way to roll snake eyes. But there are 4 ways to roll whatever you want to call this. And it could be that Bertha's a girl and the rest of them are boys, or Mary's a girl and the rest of them are boys, and so forth and so on and so forth and so on. So everybody understands why that 4 has to be there? Good. So this is going to be 0.0009. So this should be, I think, is it 0036? Is that right mathematically?
Yeah.
Okay, fantastic. Should you expect that? Now I said Max into the store with a box. I said go buy four birds, and he comes out. Should I expect a girl and 3 boys? No, it's only happened 36 and 10,000 times. I mean, it's 36 times more likely than this, but it's still not likely. Right? Is that fair? I mean, you shouldn't see a box that has more roosters in it than hens so far. Anyway, it's very, very small. These 2 together are less than a 1% chance of happening. So it's pretty unlikely. Okay? Are we so far? Okay. So, what'd you do next? Did you just go in order, or did you guys jump around a little bit?
I went order.
You went in order? In order? Good, so we're doing 2. All right, help me through it.
0.9 squared.
0.9 squared?
And then 0.1 squared.
0.1 squared? I agree with that. Are you seeing a pattern in the exponents? That's beautiful. That's part of what you're learning about right now. The binomial random variable is that pattern in the exponents. Okay, good. How about out here?
6.
6? Why 6?
Because he did it in 6.
Because Tony did it and we trust Tony.
No, because we know the paper.
Oh, I did.
I thought you were putting his tattoo.
No.
On his paper. Oh, he wrote. Oh, Tony, you wrote out all the possibilities. Give them to me.
Boy, boy, girl, girl.
So it could be boy, boy, girl, girl.
Boy, girl, boy, girl.
Boy, girl, boy, girl.
Girl, boy, girl, boy.
Girl, boy, girl, boy.
Girl, girl, boy, boy.
Girl, girl, boy, boy, which is the opposite of this one if you look at it.
Girl, boy, boy, girl.
Girl, put the boys in the middle.
And boy, girl, girl,
Or
boy.
put the girls in the middle, and there are no other ones? That's it, it is 6, yeah. That one's the hardest one to think of, is why it's 6. It's very easy to call it 4. Very easy to call it 4. It is 6, and it's tricky. That's why I like having the pictures up on the screen up here, because we can point to them now. So, what I want to do is, I want to revisit that. Thank you, Tony. And thank you, you put him on the spot. That was good.
Oh, yes.
So what I'm going to do is, I'm going to point to where the girls are with my two fingers. All right. First, I'm going to let Bertha be a girl. So if Bertha is a girl, then here's one possibility for the girls, right? Bertha and Mary.
Yes.
It could also be Bertha and Nancy, or it could be Bertha and Marge.
Yes.
So those are all the ways that Bertha can be a girl. But what if Bertha's not a girl? What if Mary's a girl? Well, I don't want to count Mary, Bertha again. We already counted them once, right? So how about Mary, Marge? So that's up to 4 now, right? How about Mary, Nancy? But that's making Mary be a girl or Bertha be a girl. What if neither of them are girls? Well, then it's only going to be Marge and Nancy. So now you've got 6 outcomes, right? You get your 6 outcomes right there. That does get to be a pain in the butt to figure out, yes? We'll come back to that. There's a reason I just gave you that program. It's because that gets annoying after time to figure out those multipliers. But for right now, I'm glad you did it. I'm glad we kind of suffered through that. So those are all the ways to have 2 girls and 2 boys. Very nice. What does that work out to be mathematically, friends?
0.0486.
486? Yeah, that makes perfect sense. That's 0.81 times 6, 486. Yes. 0.0486. Should you expect that? It just snuck in under 5%, didn't it? It just snuck in under 5%. Remember, that's that cutoff rule for outliers that's often used in industry is 5%. That snuck in, and that's when I started getting nervous, when I knew that. Because it's unusual, but just barely by that 5% definition. So then I started getting nervous about this. Because these are going up, aren't they? So then I started getting nervous about what this is going to be. So walk me through it. Help me quell my nervousness.
Okay, 0.9 to the third.
We got 0.9 cubed. Hopefully you're seeing that, 3 girls.
And then 0.1.
You gotta get the boy in there, right? The 0.1 gets the boy in there. Multiplier? 4. This is gonna be the same. This has to be the same as this. Because here you pick the place the one boy has to be. Or excuse me, the one girl has to be. Here you're picking the place the one boy has to be. It's the same logic. The same logic. Except the difference is over here. So what's that? 7 to 28-ish?
29.16.
29.16?
Yes,
Yeah.
Yeah.
Yeah, 29.16.
There we go. And that's when I'm like, oh God, 29%. That's pretty common, isn't it? That's 29% is 29 out of 100. That's about 1 in 4. So that means for every 4 times I send Max into the store to buy 4 birds, one of those 4 roughly, he's going to come back with a boy and 3 girls in the box. And I start getting old. I'm like, oh God, I live in a neighborhood. My neighbors already don't like me. I have a rooster maybe. So I kept going. And Sarah, we could do it Sarah's way, which I love. Because Sarah says, I know these all add up to 100%, yes? You know that. So you could just add up what you've already got, subtract it from 100 to get what's remaining, correct? You could totally do that. But it's almost as easy to do it the way I'm about to do it right now, which is just...
0.9 to the 4th.
And the reason I like doing it this way is this is what I did in the store. We'll come back to that in a minute. What does this come out to be?
0.6561.
6561? What's the multiplier? Good 1. There's no extra number to put in because it really is just a 1. You got it. Because it's like rolling snake eyes again. There's only one way, they're all girls. You can't mix them around, they're still going to be girls. So this is, remember what I said when I went into the store and I said, you mean there's a 1 in 3 chance there's a rooster in this box? This is the number I quickly calculated in my head. I didn't get it down to this precision that you guys did. I did 0.9 times 0.9 in my head. So 0.9 times 0.9 is 0.81. I dropped the 1, I called it 0.8. Then I did 0.8 times 0.8, which is 0.64, which is essentially what this is. And 64, in my mind, this is my mind, is close enough to 2/3, because 2/3 is 67%. So 64, 2/3 of the time, this is going to happen. So 2/3 of the time, 65.6% of the time, you're going to get all girls. So if 2/3 of the time you get all girls, what happens the other 1/3 of the time? There's got to be a boy in there somewhere. And that was my only statement. There's a 1/3 chance there's a rooster in this box. And this is what I said. I sat down and did this with the guy at the store, and he was totally enthralled by it. This is the coolest thing I've seen all day. I'm like, you got a store full of chickens, dude. This is not as cool as that. But he was totally into the mathematics of it. I love when math makes people happy. Usually it just pisses people off. But this is a real thing to think about. Think about it a different way. Think about it a different way. What's the probability one of the little birds is a girl? Just one of the little birds? One of the little birds. Birds is a girl? 0.9, right? So that means 9 out of 10, right? 0.9 is 9/10. So 9 out of every 10 birds is going to be a girl. So if I send Max in 3 times to buy 4 birds each time, he's bought 12 birds altogether, right? Doesn't it stand to reason one of them should be a rooster? If it's 9 out of 10, the other 1 out of 10 on average is going to be a boy. If he buys 12, he's bought 10, which means there should be a rooster mix somewhere there. This is why I'm being a little irrationally nervous about the next 4 that I just bought. Because now I've got 8, right? Now I've got 8. So I'm irrationally being nervous about that because I'm pretending that the chickens have a memory. And then the next 3 years from now I buy 4 more and then I have to start getting ready to make rooster soup. So, cool?
But didn't you go back and return 2?
Well, not because they were boys. Because
No,
Fern
I know.
1 was pecking the other one's eyes out.
So you've had 14.
But you
Oh,
banned
shit.
Or no, 8, 9, 10. So you've had 10.
So I've had 10. Ah, crap. I returned a rooster. I know I did. It's a 1 in 5 chance. Damn it, Linda. Maybe the reason Fern was being aggressive was because she was a boy. Jesus. Now, just real quick, and I'm going to let it go for a quiz for next week. Those numbers that I did in green right there, the 1, 4, 6, 4, 1, these are called binomial coefficients. You'll understand why they're called binomial in a minute after break. Do you remember the other ones we came up with yesterday? So this one's 1, 4, 6. How do you think of this? Excellent. 1, 4, 6, 4, 1. You remember the numbers when we had a flock of 3? It started with 1, and then it was
1, 3.
3, 3, 1. Remember those multipliers from yesterday when we only had 3 girls? So this is a flock of size 4. This was you don't have to write this down. This is just an introduction to a quiz for next week if you want to do that quiz, and you might decide right now if you want to or not. When there's a flock of 2, it was 1, 2, and then 1. That was when we first discovered we had to put the multiplier in there. The first flock, when there was only 1 bird, you didn't really have any multipliers. They were both 1. This is a very special array of numbers. Because if we had 5 birds in the flock, if I added a 5th bird, I would know what the next line of numbers is by simply looking at the row above it. It would be 1, 5, 10, 10, 5, 1. The reason I know that so quickly, can you guys see the pattern between the row above it and the next row? So what's the pattern between here and here? How did I know that was 5?
1, 2, 3, 4, 5.
Oh! Another pattern that's in there. The diagonal is sequential. Very good, very good. The way it's actually generated the whole thing, you see it there?
Yeah, you add the first two together.
1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. Yes? Pascal's triangle. It's this guy Pascal, he's coming up. Pascal's wager, Pascal's bet, Pascal's triangle. Why is it called Pascal's triangle? Because the Chinese had it 2,000 years before him. And somehow his name got attached to it. I don't know how that works. But anyway, it doesn't matter. The next row, you could find the exact same way. Go with me. 1, 6, 15, 20, 15, 6, 1. You can see how annoying this is going to be. If you have 6 birds in the flock, there are 20 ways to split the genders, 3 boys, 3 girls. Imagine doing that with 6 pictures. Okay, Marge, Bertha, Mary, Marge, Bertha, Marge, Nancy. You're going to lose track, right? So this continues forever. It goes on forever and ever and ever and ever. I got a whole quiz based around that if you're interested for next week. Go ahead, Zach.
I don't understand the relationship between like 4, 6, and 5, 10, 6, 15.
Just that each element here is gotten by adding the 2 diagonally above it.
Got it.
And the quiz explores that as to why that makes sense. I don't want to get into it in class because it's going to derail us away from the big idea, which is the distribution itself. But it also is a nod to the fact that making these by hand can get pretty in-depth. Fair enough? What I'd rather do after break is I want to do a big picture analysis of the whole distribution. It's called something special. It's called a binomial distribution. We'll talk about why momentarily. And I'm going to show you how to run that program and how we use this particular distribution to do wonderful things with. But let's take 5 first, yes? This is fun stuff. Super fun stuff. It's beautiful. A lot of patterns in it, a lot of neat results in it. But that's what the quiz is for if you want to go down that road and explore it. It's definitely more of a math geeky kind of quiz, which is why I like it. So, cool? Let's take 5. Yes, let's take 5. Yes, Pascal's all over the place. He invented probability with Fermat, Pascal's wager, Pascal's triangle, and it's crazy stuff, crazy stuff.
Kilopascals.
Yeah. Yes, 0 birds. Okay? Exactly. That's one of those other justifications. I didn't know that project was always so dense. I can put it in the project where I can make myself an independent quiz. And I really wanted you guys to think hard about why it's 1, rather than just complete the pattern like, but why is there 1? There's no things. Exactly. So that's what I wanted you to